LAN unit would. Um, so go through these. So group pathfinding. So this is the idea of grouping. So right now we have 4 units that are kind of in a general pattern already. They're kind of organized. And so one way we could deal with this is actually to have them go one by one along an optimal path. It doesn't really look realistic. It'll get the job done, but realistically, you're not going to say, okay, let's all line up and go single file along the path. You're going to stay in the formation that you've been in before. So this is an example of that. So you have your optimal path. You have your different units in their formation. You can just offset their movement from the path by a small margin so that they wouldn't collide with each other, and then they can move kind of in a more intelligent manner, along the path instead of something that looks awkward. There is a problem with this in that when you encounter obstacles, you have to plan for that in your pathfinding. So it adds a little bit more computation to finding the correct path. So as you're moving along, you have to keep in mind kind of the radius of the units that you're using. So in the first example, you're kind of cutting it too close to this object, and one of the tanks will collide with it, so that won't work. If you had just found a path slightly further away from it, it would work fine. Another problem you might run into is if there's a constraint whereby there's a bottleneck. In that case, you might want to code your AI to kind of break formation for a small period of time. I mean, in this example, maybe there's only 1 or 2 paths through this obstacle, and so you would search around to see if there was a better path, but at some point it becomes computationally expensive to go any further, and so you just give up and say, all right, break the formation, go forward through this path. You don't want to waste your time, looping all the way around the map if this is really the best solution out there. And we talked about kind of having that cost of having units move out of your way. You could use a similar thing here where you could basically add the cost of the bottleneck into your path finding algorithm, and then if you haven't found anything within a certain distance, say, okay, this is really truly the best path to use. And you go through the obstacle and you can return to your original formation. Okay. So then the last concept in this chapter, which is hierarchical pathfinding. So on the left-hand side, we have a very complex path node. Okay, it's still pretty simple, but you can see that it's relatively complex. You have more nodes in each area than maybe you really need. And that's great because it gives more freedom to the units in those areas, and you could imagine that maybe in a more complex game it would be even further. Maybe there's 100 nodes in each one of these separate areas, allowing units to go all over the place. So that's great because on one hand you get lots of different movement, you get lots of variation for the player. It doesn't look like they're always standing in discrete spots. They can move wherever they want. The problem is that with all those nodes, it's really unclear how you should traverse through there. So you wind up spending a lot of time computing how to move from relatively close points. So let's take a look at the example on the left where you have point E and F. So you can see E and F are relatively right next to each other. But you could imagine that if there were a lot of nodes here in the area that E is inside, you could spend a lot of time trying to find the one opening through here, and then a lot of time finding the opening through here, and a lot of time wasted just trying to figure out that this is the optimal path. And the alternative to that is having basically a simplified path node structure, whereby you can kind of like designate areas and say, okay, you can move from this section to this section and that section. So it takes a little more computation time pre-computing this, but the savings for computing it real time with the more complex path node system is far outweighed by the savings that you're going to get from actually using this. And so what you could do is kind of have abstract distances. You could figure out that, okay, come up with some sort of deterministic simplification of what the paths are. So let's just kind of not arbitrarily, but come up with lengths for these paths that represent how difficult it is to get from one spot to another. So now, in this case, is going from E to F. You know, okay, well, the best path is H2 to H6 to H7 to H4 to H3. So you would maybe only consider the nodes in H2, H6, H7, H4, and H3 instead of trying nodes over here, and over here, and over here, and over here. So you simplify how many comparisons you have to do. Alternatively, maybe you can just do a couple in each of these. So it really just saves yourself some time by eliminating a lot of structures, and it gives you eliminating a lot of the nodes that you're not going to compute. It gives you the best of both worlds. You get the fast runtime algorithm that eliminates as much data as possible, while at the same time, those movements in those areas are the most complex that they can be, given the path node that you have. And so that's what I was saying, that, you know, based on this, you can figure out which nodes you want to actually expand upon. Like that. So in this case, you're going from A to Z, you only need to consider the ones in between. And so in this case, it was an elimination of about half of them, but in a much bigger node, you could imagine it would be a much greater savings. So in summary, we talked about, you know, the performance optimization of pathfinding that you can do, figuring out different zones that you can go to, pre-computing that rather than trying to determine it on the fly. This will let you know if you're absolutely going to fail, and lets you know if your algorithm is written correctly. We also talked about virtual players and waypoint paths. So rather than just always searching for long paths, you can search for shorter paths, which will give you a better runtime experience. It'll work more efficiently. You will actually spend less time trying out the nodes that are further from the path that don't really get you where you want to go. And so that's one more optimization that you can use. Group pathfinding saves time in trying to figure out a path for multiple units at once instead of trying to do 4 pathfinding operations at once. You can just find one for the group. There are some problems with it, but you can design around those in your code. Hierarchical pathfinding, so this is the last concept where rather than just always looking at the entire node structure that you have available to you, you can limit it to certain areas and have kind of a, very similar to the waypoint, have an abstracted version of it where you can just determine what's going to be roughly the right path and then expand the nodes that are in those areas and then find the correct path, thus eliminating a lot of unnecessary checks. So that is chapter 7. Do you guys have any questions about either this or stuff that was related to chapter 6?
Did you print out that homework, the homework thing that you went over first?
What was that?
Did you print out the answers or send out the answers
Yeah.
for the last one?
Sure, I'll post them up on the website tonight. So now that I've gone over it. Okay, so then the very last thing I want to go over is some of the code that I wrote for project option number 2. So project option number 1 I think is pretty straightforward. The book does a really good job of explaining what's going on. Project option number 2 is a little more open-ended, and so last time during the midterm we kind of went over it a little bit. But I've got a couple of different presentations that I can talk about, a couple things on Wikipedia, so I can kind of try and explain a little bit better what's going on with that one and how you might tackle it. I also put up some basically like code templates for how I would attack the problem, so you can take a look at that and see if maybe that helps give you guys an understanding of how you can approach this. So, alright. What do I want to bring up first? I'm going to go with this. So, these are some of the links that I have as the reference material for project option number 2. So this is a book that I really like. It's a little more in-depth and covers some stuff that we don't really need to in this class, but it's a good resource. I don't really remember what the name of the book is right now, but it's listed in the both on the website as future reading or additional reading if you want to, and in this project option number 2 write-up. So basically, I'll just start from the beginning. So project option number 2, your task